Oh, yeah. All right, so 9.1, sequences and series, convergence and divergence. So we've already talked about convergence and divergence. What does convergence mean? If something converges, then it what? It goes to a finite number. It approaches a finite number, and if something diverges, yeah, it either goes to infinity or negative infinity, or it could actually diverge by oscillation as well. It just does not approach a single finite number. So what we're going to be looking at now is kind of, we finished building the first half of the house of calculus with derivatives. We finished building the second half of the house of calculus with integrals. And now we're completing with the house, and now we're going to build a shed out in the back. Okay? So it's kind of an attached thing, sequences and series. And it's good for like putting your garden equipment. So we're going to start with sequences, and then we're going to transition into series. So first of all, a sequence, much like in English, is just a list of things. Okay? Something, comma, something, comma, something, comma, something. And in English, there doesn't have to be any rule that generates the sequence, right? I like peas and carrots and brass bells, right? I didn't see that last one coming, but that would be a sequence, right? In mathematics, there is a rule that generates the sequence, and we call the terms or the things in the sequence, we call them terms, and we separate them by commas, much like we would do in English class. So, for instance, oh, it's frozen. Okay. For instance, if you look at the set of natural numbers, right, which we denote as the double bar n, then we can say little n is an element of the natural numbers as long as it's in this sequence. So we use a brace typically to denote the set. The elements in the set then are the terms. 1, comma, 2, comma, 3, comma. And then we put dot, dot, dot. Why dot, dot, dot? It continues the pattern. Good. And the pattern is the important thing, because if you're not given an equation to generate them, you need to establish the pattern sufficiently by expressing enough terms so the pattern is established. Anybody going to doubt what the next number is after 3? 4 is good. That's the right answer. If I just put 1, comma, 2, would that be enough to establish the pattern? Probably not. So 3 would be like the bare minimum. The more sophisticated the pattern, the more terms you need, all right? Certainly if I just said 1, comma, you wouldn't know the pattern. So we can denote a sequence in this manner. We can denote a sequence by listing, like a roster, a sufficient number of terms in the sequence separated by commas. Sometimes we can generate the terms by what's called a rule. And instead of using like function notation like f of n, we typically use subscript notation. A sub n is what we call it. A sub n then is going to be called the nth term in the sequence. So a sequence could be written like this. You'd have a sub 1, comma, a sub 2, comma, a sub 3, comma, dot, 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 comma, a sub n, comma, dot, dot, dot. All right, and so what does this mean? The subscripts become what we call the index, and it's a way to keep track of which term we're on. So a sub 1 is the first term, a sub 2 is the second term, so on and so forth. A sub n would be the nth term. Now this sequence, much like the natural number sequence, are infinite. Yes? Infinite. Which we know what that means now, right, Megan? Infinite. It's interesting. It means not finite. So that's what we're going to be concerned with. Infinite sequences, things that go on forever and ever and ever. And we are going to concern ourselves with whether or not these sequences do what? Guess what? Converge or diverge. Yeah. All right. So sequences, real quickly here, can be expressed by either an ample, sufficient number of terms in the sequence, separated by commas, an explicit function, like we just set up above. We call that the nth term. It's also known as the rule of sequence. So the nth term and the rule of sequence are kind of interchangeable, or the rule of sequence set off in braces. So sometimes you'll see it like that. But we typically use braces for sets. Okay, so example 1, the sequence 2, 4, 6, 8, comma, dot, 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 is a sequence of even numbers. Express the same sequence as a rule for a non-negative integer n. And typically n is an element of, not z, sorry, the natural numbers. It's a non-negative integer. Sometimes it could be 0. But usually n is a counter. It keeps track of which term we're on, and we usually start with the first term. All right, so what I want to do is list that as a rule. So I want a sub n to equal 2, 4, 6, 8, comma, dot, dot, dot. Now that implies that it goes on forever. But sometimes we can do it like this as well. Okay, so I'm sorry, let me back up. I can list the sequence like that, a sub n equals. And it doesn't have to be set off in braces, although it can. All right, if it's typically equal to a sub n, we kind of interpret that as a sequence. If it wasn't equal to a sub n, then it would be in braces. And there's another way to denote it. You could do 2, 4, 6, 8, comma, dot, 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 comma, a sub n, comma, dot, dot, dot. And that's another way to denote the sequence, but the rule would be written out here. And that's what we want to find here. I want to figure out a rule in terms of n that'll help me generate these terms. That is an explicit formula. So this would be n equals 1, this would be n equals 2, this would be n equals 3, this would be n equals 4. I want to come up with a formula, a function as a function of n that will allow me to generate the nth term without doing it recursively. What does recursively mean? A lot of vocabulary here. Recursively means that we rely on the previous terms to generate the next. So 2, 4, 6, 8, what are we doing each time? We're adding 2. So if I want the 50th term, I don't want to have to generate the first 49th and just add 2, right? That would be a lot of work. So can we come up with a formula then that'll allow us to generate the nth term by plug and chug? Yes. What would it be? Well, how about just 2n? Does that work? If n starts with 1, then when n is 1, what do we get? 2. When n is 2, we get 4. Okay? So the new Algebra 2 textbooks call this f of n, which is fine. This is like a function. But unlike f of x equals 2x, we are not using all real numbers. We are only counting by whole numbers. So we start at 1, we go to 2, 3. And so we typically don't use f of n notation. We use a sub n. And that is kind of implied that n is a natural number. All right? So there you go. So you can write the sequence then like that. You could say it's this. You could even say it's 2, 4, 6, 8, comma, dot, 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 comma, 2n, comma, dot, dot, dot. A lot of different ways to do it. But a sequence is a list. It's a list that's generated by a rule. And the rule can be explicitly given by a formula, like 2n, or it could be a sufficient number of terms to generate the pattern. It's not always easy or possible, really, to come up with the explicit formula for generating the nth term. Sometimes the only way to do it is maybe recursively. Okay? So let's jump to this one here. We have a sub n equals, in braces, 4n over 3 plus 2n. So this is a sequence, all right? And we want to know, ultimately, what is the limit as n goes to infinity of a sub n. That is the way to determine, then, if the sequence does what or what? Converges to diverges. We're just going to let the number of terms approach infinity and look to see what the terms do, okay? Now, let's go ahead and list out the first few terms. We could say that that equals, and again, n is a natural number, so we're going to start with 1. It's a counter. First term, second term, third term. So if we start with n equals 1, what do we get? 4 over 5. Good. Comma, when n equals 2, what do we get? 8 over 7. Good. When n equals 3, we get 12 over 9, comma. Now you can almost generate the terms now without plugging them into the rule, right? Yes. You can simplify 12 ninths. You can simplify. Sometimes when you're generating patterns, though, let's simplify at the end. We want to generate the first 5 terms. Without looking at the rule, can we generate the next term? Yeah, we're adding 4 in the numerator. So the next one will be 16, and we're adding. Yeah, we're adding 2 to the previous number, right? So on the top we're adding 4 to the previous number, and on the bottom we're adding 2 to the previous number. So that would be 11. So that would be the recursive nature. We're relying on the previous number to generate the next. We're adding 4 on the top, we're adding 2 on the bottom. So the next one would be 20 over 13. Yeah, comma, dot, dot, dot. So the Holy Grail would be to find an explicit formula, which is what we started with to generate it. Yes, now if you want to simplify that, feel free. 4/5, 8/7, 12/9 simplifies to 4/3, 16/11, and 20/13. If I gave you something like this to start with and I asked you to find the explicit formula that generates the terms, that would be a much more difficult task. Okay? It's made even more difficult by the fact that the third term is now simplified. But you would start by realizing that maybe it's +2 + 2 + 2, and then +4 + 4 + 4. This is what we call an arithmetic sequence. When something increases by a constant, either additive or subtractive, it's going to be arithmetic, which means that the number that's being added or subtracted ends up being the factor. It's going to be that number times n. Okay? So that's where the 4 and the 2 come in, and 3 is just our starting value. So I don't know if you studied arithmetic sequences in Algebra 1 or 8th grade or whatever, but arithmetic, they increase by a constant number difference, we call it, and it turns into a multiplication rule. Okay, so the goal is to figure out if this thing converges or diverges. So if I ask you then to take the limit, the limit as n goes to infinity of 4n over 3 plus 2n, that would be very analogous to the same thing as the limit as x goes to infinity of 4x over 3 plus 2x. The only difference is n is counting by positive integers and x is counting by real numbers. What would the answer to this one be? 2, right? You would say, oh, the top is linear, the bottom is linear, they're growing at the same rate. So without L'Hopital's rule, we know it's just leading coefficient over leading coefficient, which is 2. Do you think it's going to be any different over here? No, it's not. Okay? The numbers are still getting infinitely large. We're just jumping by positive integers instead of going through a continuum. So luckily, it's the exact same skill set. We're just using n's for natural numbers instead of x's for real numbers. So this sequence converges, which means that if you go out infinitely further and further and further, the terms in the sequence will get infinitely closer and closer and closer and closer to the number 2. But they won't ever get there, okay? So this is a convergent arithmetic sequence, we would say. Fact! If a sub n is the sequence or the rule of sequence for the set of real numbers, here are the possibilities, okay? And by the way, since n is a natural number, we're only going to be taking the limit as n goes to infinity, not as n goes to negative infinity. We're not going to be counting backwards, okay? So what are the possibilities? Well, the limit of the sequence could equal infinity. If that's the case, then your sequence gets infinitely larger, and we say it diverges to infinity. If your sequence gets infinitely small and negative infinity, then we say it diverges to negative infinity. In the case that we just saw, if the limit equals a finite number c, then we say that the sequence converges to c. And then the one that I mentioned to start the class, you could actually have something oscillate between 2 fixed values, in which case we say it diverges by oscillation. So there's more opportunities, I guess, or ways it can diverge than converge. Definition. This is a very important thing. I tweeted about it this morning. N exclamation point is read as n factorial. Okay, it's a mathematical operation. And it is defined recursively like this. N factorial is n times n minus 1 factorial. What the heck does that mean? It means that 7 factorial is equal to 7 times 6 factorial. Well, what is 6 factorial? Well, 6 factorial then, recursively, is 6 times 5 factorial. Well, what is 5 factorial? 5 factorial is defined to be 5 times 4 factorial. So if you keep going all the way around, all the way down, 7 factorial is really 7 times 6 times 5 times 4 times 3 times 2 times 1.
Times 0.
Yeah, you stop at 1 because if you went all the way to 0, then every number exclamation point would be 0, right? So this is a pretty common thing in probability, right? If you have 7 shirts, how many different ways are there for you to pick 7 shirts? Well, hang on, that's not right. Yeah, that's wrong. No, yeah, that's wrong. I'm just thinking of shirts for some reason. Let's say that you have a 7-member committee, and you have at least 7 people that are going to be on the committee. How many different ways can you form the committee? Well, there's 7 ways for the first person to be chosen. Let's say you have 7 people. 7. Okay, that's still not right. That's still not right. Let's do Battle of the Bands. You have 7 bands competing in a Battle of the Bands, and you're going to award 1st through 7th place. Okay, how many different combinations of orders of those 7 bands can there be? There's 7 ways to choose the top band, right? That leaves 6 bands left over for 2nd place. So there's 6 ways to choose 2nd place. Now that the 1st and 2nd place are determined, now there's 5 ways to choose 3rd place, 4 ways to choose 4th place, 3 ways to choose 5th place, so on and so forth. So these are independent events. If you multiply them all together, that gives you the number of combination of 1st through 7th places. That's a big number, right? So that's why the factorial is kind of a necessity, because these things show up a lot in probability, and they also show up a lot in sequences and series. So let's look at this. This is an interesting fact. What is 2 factorial? 2, right? What is 1 factorial? 1. What is 0 factorial? 1. Yeah. Okay, so that was the tweet this morning. 0 factorial equals 1 factorial. But 0 does not equal 1, right? So it's almost like if you say it emphatically enough with the explanation, 0 equals 1. Okay, all right. Have it your way, right? And makes them equal, right? That's equality by brute force. But it also works mathematically. Why is 0 factorial equal to 1 factorial? Very good. If you look at it in terms of combinations, the factorial is the number of ways to arrange n objects, which was why it finally worked with the bands. There are 7 factorial ways to arrange 7 bands in order. Okay? So 1 factorial is the number of ways to arrange 1 object. How many different ways can I arrange my 1 iPad on this shelf? 1. There it is. Okay? So 1 factorial is 1 way to do it. How many different ways are there to arrange 0 objects? There's only 1 way to arrange 0 objects, right? You can't. Now, it also works mathematically. Here's why. If you look at the recursive relation, 1 factorial recursively is equal to 1 times 1 minus 1 factorial. Yes? That's what this says. 1 factorial is equal to 1 times 1 minus 1 factorial. Well, let's simplify that. That means 1 factorial equals 1 times 0 factorial. What's anything times 1? Itself. So 1 factorial equals 0 factorial. And there it is. There's the mathematical proof. Pretty sweet. So we'll be using factorials a lot. Okay, example 3. Very quickly moving on. Determine whether the following sequences converge or diverge. If they converge, we're going to figure out the what. So if I just gave you the first 4 terms, 1 over 2, 2 over 3, 3 over 4, 4 over 5, you could probably generate the next term. But would you be able to come up with the rule of sequence? Maybe, maybe not. It is n over n plus 1. What happens to this sequence then as n goes to infinity? It approaches 1, okay? And here would be the work that you'd show. The limit as n goes to infinity of n over n plus 1 is 1, because it's 1 end of the first over 1 end of the first. So to determine whether a sequence converges or diverges, it's really, really, really helpful to have the nth term equation or the rule of sequence, because without it, you're kind of just guessing, right? 4/5, and the next term would be 5/6, 6/7, so on and so forth. You could maybe think that it goes to 1, but when you have the rule of sequence, the function essentially, then it's indubitable. Indubitable. Is that a word? Indubitable? Okay. Indubitably is the adverb. Okay. How about this one? 1 over 2, 1 over 4, 1 over 8, 1 over 16. What's the pattern? We're just multiplying by a half each time, right? A half times a half is a fourth, times a half is an eighth, times a half is a 16th. This is called a geometric sequence. Anytime you're multiplying or dividing to get the next term rather than adding or subtracting, it's called a geometric sequence. It's kind of like exponential. Okay, so the formula is 1/2 to the n, or it simplifies to 1 over 2 to the n. Does this sequence converge or diverge? it converges pretty rapidly to what? 0, right? It's kind of the same idea. The top is always the 1. The bottom is exploding really, really rapidly. It's getting pulled down to 0 very rapidly. So the sequence converges to 0. Letter C, how about this one? Ah, very good. This right here, you're going to become very familiar with. This is called an oscillator. The C is usually silent. An oscillator. And here's why. It contributes really nothing magnitude-wise. It only contributes a sign. In this case, the sign of 1. When n is 1, it's going to be a negative. When n is 2, it's going to be a positive. When n is 3, it's negative. So this is either a 1 or a negative 1. So if you want to start listing some of the terms, when in doubt, list them out. The first term when n is 1 is what? 3 minus 1, which is 2. The next term when n is 2 is going to be 3 plus 1, which is 4. The next term when n is 3 is going to be back to 3 minus 1, which is 2. When n is 4, negative 1 to the 4th is positive 1, so it's 3 plus 1, which is back to 4. And now you can really see the pattern, right? It's 2, 4, 2, 4, 2, 4. So this one does diverge. Yes?
So the calculators for like sine, cosine, do they have a series like programmed in? So that's how it's called.
I'm sorry, what? One more time?
Like the calculator, do they need like an actual formula to solve it, or do they use zero for sine, cosine?
To solve what for sine or cosine?
Like if you were like, you said like sine of 3, like if they use a series to solve it?
Oh, that's a good question. How does the calculator find sine of like funky angles that aren't on the unit circle? I don't know how it's programmed. That's a good question. If you're doing sine of a whole number like sine of 3 or sine of 4, the series might work. But I don't know how it would do like sine of like 3.7 or something like that. There's a way that it's programmed to do that. But sine and cosine themselves oscillate between 1 and negative 1. And we'll talk about another type of oscillator there. Okay, let's look at this one over here. A sub n equals n over 1 minus 2n. What is the limit as n goes to infinity? Negative 1/2. Yeah, negative 1/2. So sequences can converge to negative numbers. That's fine. This one here. What is the limit as n goes to infinity of, I'm just going to write a sub n in this case. 0. Kind of the same idea, right? We don't need L'Hopital's rule here. It is infinity over infinity. If we just realize then which one grows faster, any linear function, n grows faster than a log function. So it does go to 0. Okay, how about this one? N over n plus 2. In the hierarchy, let's review the hierarchy of growth. You have constants, and then you have log functions, and then you have power functions. I'm just going to use x again, x to the nth power. So like x squared, x cubed, even x to the 1/2, x to the 1/3. And within each family, there's their own hierarchy. So for x to the n, the bigger the n, the faster it converges. After that, we have exponential. So b to the x powers. And again, the hierarchy is the larger the base, the faster it grows. And then after that, if you remember, we had, well, even before that, we have factorials. Okay? Now, x factorial for real numbers doesn't make sense because we use integers. But they grow faster than exponentials. Factorials grow faster than exponentials. And then x to the x grows faster than factorials. Okay? So that's where the factorials fit in the whole scheme of things. Anything to the right grows faster than anything to the left for large values of x, or what we're going to be doing with n. But these are both factorials. So they're kind of growing at the same rate. And we don't have a lot of experience with it. So here's what we could do. If you ever have the quotient of 2 factorials and they're both in terms of the same n, you can put them in terms of each other by using the recursive formula. Which one's bigger, n or n plus 2? N plus 2, right. So let's go ahead and start with the bigger one and start writing it down. N plus 2 factorial then is n plus 2 times, what would be the next one? N plus 1, right? We keep subtracting 1 every time. N plus 1 times, what would be the next one? N, and then n minus 1, n minus 2. Once we hit whatever is in the other side of the equation, or the fraction, in this case n factorial, will stop. We essentially tie off the process with the factorial once these matched. And why is that nice? What happens with n factorial divided by n factorial? They divide out. So this is now equivalent to 1 over n plus 2 times n plus 1, which means now we take the limit as n goes to infinity of a sub n. The top is a constant, and the bottom is effectively a 1n squared, right? Which means the bottom grows faster than the top, and this goes to what? 0. Yeah. So there's the hierarchy in your factorials. If it's a larger factorial number to start with, it's going to go faster than a smaller factorial to start with. And then, God, we're not going to finish before lunch, but let's see. 2n factorial over n minus 1. How are we going to do this one? Same way. Yeah, if you're not sure, the 2 goes along for the ride. N or n minus 1 is larger? N. So we're going to start with the larger one. That's n times the next one would be n minus 1. That's what it has on the bottom. Tie it off. We'll finish this. Your n minus 1s divide out. This is now the same as 2 times n, which of course does what as n goes to infinity? 2 times 1, 2 times 2, 2 times 3. This grows infinitely large, right? This diverges to infinity. Okay, we'll pick up with H and see if we can pick up the pace here a little bit after lunch. We definitely want to get to series today. So have a good lunch, and we'll see you when you return.